We present our work on ego motion compensation of range-beam-Doppler data for object detection. More and more publications are solving radar perception tasks on this data level. Surprisingly, in past publications, the Doppler information of this data has only played a minor role, even though velocity is considered a powerful feature. We investigate the hypothesis that the sensor ego velocity induced by the ego vehicle motion increases the data generalization complexity of the range-beam-Doppler data, and propose a phase shift of the electromagnetic wave to normalize the data by compensating for the ego vehicle motion. A chirp, which is a signal in which the frequency is increased, can be used to determine the range to an object. The phase difference of multiple consecutive chirps, which is caused by the Doppler effect, can be used to calculate the relative radial velocity of that object. The measured phase difference between two consecutive chirps is actually a superposition of the radial velocity of objects in the scene and the components of the ego velocity in the direction of the objects. The ego velocity in the direction of the object is dependent on the angle, is dependent on the beam. On the right, you can see the algorithm that is used to compensate for the ego vehicle motion. The vehicle velocity, together with the mounting position of the sensor, is used to calculate the velocity of the radar sensor. Then, for each beam, the speed in the direction of that beam is calculated, which is then used to calculate the phase shifts it introduced in each chirp. Finally, the radar signal is shifted to compensate for these phase shifts. When the indices of the highest magnitudes of the radar tensor data are visualized in a scatter plot, without ego motion compensation, the Doppler channel depends on the velocity of the data recording vehicle. After ego motion compensation, all static objects have the Doppler channel equal to 0. And even objects that are partially occluded in the camera are very apparent in the plot. We train and evaluate object detection networks on the data, once without and once with compensating for the ego motion. For a network which is only using this radar data, the average precision improves by 8.7 percentage points. For a network that is based on radar camera fusion, the performance improves by 3.5 percentage points. While ego motion compensation has been a common approach for radar point clouds, we demonstrate that it is also important when range-beam-Doppler tensors are used. We present a mathematical formulation of how to compensate for the ego velocity and demonstrate the effectiveness of this approach in an object detection task. Thank you.